In this video, we're going to use the arc length formula to find the length of some arcs. So in this example here, we have the function 3 natural log of x minus x squared over 24. And I just want to know what's the length of that curve along the interval 1 to 6. And this is really easy. You just shove it into the formula written above me. In the previous video, I tried my best to explain where that came from, but now let's just show how to use it. And really the only trick, maybe the complicated thing in these types of problems, is recognizing perfect square trinomials. So that's the hardest thing, I think. Okay, so here's my function, my f of x, and I need a f prime of x. So I'm just going to simply take the derivative of this to find y prime or f prime. Well, the 3 is just a constant, it just stays there. The derivative of the natural log of x is 1 over x. The 1/24th is just a constant, I can pull that out front. The derivative of x squared is you bring down the 2, you rewrite your base, and you subtract 1 from the exponent. I'm going to clean that up a bit. Y prime, or maybe I should call this f prime of x, is 3 over x minus, that'd be 1/12. 1/12 x. All right. Well, then the formula says, well, you need to square that thing. You've got f prime of x, now you need it squared. So f prime of x being squared is simply 3 over x minus 1/12 x times itself. 3 over x minus 1/12 x. I like to write it side by side so that I can use my little fingers to do that FOIL or that massive distribution. That looks like 9 over x squared. That, 3 over x times 1/12 x, the x's reduce, and the 3's reduce, so I get 1/4. I get a negative 1/4. That's it. I don't believe that. One more time. 3 times 1 is 3. X over x. Yeah, I guess so. Similarly here, I have another negative 1/4. This is going to be a positive x squared over 144. Clean that up. Oh, that's minus 2/4 or minus 1/2. Okay, they gave me the function. I found the derivative. I squared the derivative. Bam. I shove it into this formula. The arc length will be equal to the integral over the interval 1 to 6 of the square root of 1 plus this stuff. dx. Now we could do this maybe with respect to y, but this function was given to us in terms of x, so and along the interval, yeah, there you go. dx, that's what we're familiar with. Okay. Well, 1 plus a trinomial I can add, and in factors-like terms, 1 minus 1/2 is a positive 1/2. So I think I'll do it something like this. Plus 1/2 plus x squared over 1/4 with respect to x. Okay, now I just need to integrate the square root of this hideous looking function. Now is when maybe we start to panic. We learned a whole bunch of integrating techniques already for this course. I cannot split that apart. This is, hopefully you just kind of recognize a perfect square trinomial. And there's a big hint because we kind of just did it with one small difference. And this is a common theme throughout these arc length problems, where you're given something and when you square it out, it becomes a perfect square trinomial. But when you add 1 to it, it changes it just a bit, but it's still going to be a perfect square trinomial. This is still a trinomial, bing, bing, bing. The first term is 3 over x squared. The last term is x over 12 squared. And that middle term happens to be double their product. But instead of a minus 1/4 or minus 1/2, we have a plus 1/2. So instead of 3 over x minus 1 over 12x, or 1/12x, we're going to have 3 over x plus 1/12x. So I claim this is a perfect square trinomial. I got my, I've got a lecture on this back in pre-calculus if you need to revisit perfect square trinomials. Look what glorious thing just happened. I had the square root of this trinomial, and I didn't know how to separate it apart. But because it's a perfect square trinomial, I can rewrite it as 3 over x plus 1/12x, two of those, or that binomial squared. So then the square and the square root kind of undo each other. Well, that was nice. I'm integrating from 1 to 6. Now a polynomial. 3 over x plus 1 over 12x with respect to x. I got this. That's just 3 times the natural log of x plus, this is going to go up to a square, multiply out front by the reciprocal of 2 is a half, so it's going to get even smaller, 1/24. But I am doing this with limits of integration, so I need to apply the fundamental theorem of calculus, plug in a 6, and subtract plugging in a 1. Oh my goodness, I did not want to do this. Minus 3 ln 1 plus 1 over 24th times 1 squared. I would probably bust out a calculator just to double check myself. The natural log of 6 is not anything clever, so I'm just going to leave it alone. 36 over 24. They're both even, so I can cut them in half. 18 over 12. Those both have 3's in them. 6 over 4. Okay, those are both even. That means I had 6 in them, or whatever. I've got 3 over 2. Whew, that was so hard to do. Plus 3 halves. Minus, now the natural log of 1 is famously 0. So I don't have to worry about that. But I am subtracting 1/24. Oh my goodness, I guess I should get a common denominator. Multiplying top and bottom by 12, that's 36, I think it's going to be 35. 24ths, positive 3 ln 6. All right, let me walk through that one more time real quick. I had a function along a interval. If I want to find the length of that function, well, I simply use the arc length formula written right above me. So I have to find the derivative and square. I think we were all comfortable with that. So I found the derivative, which was 3 over x minus 1/12 x, and I needed to square it. That is, I take 3 over x minus 1/12 x and square it. Well, that square just means that I have two of them being multiplied together. When I FOIL it out, I recognize a perfect square trinomial because that binomial times itself, that's a perfect square trinomial. Meaning if I were to factor it, it would get me down to this one binomial square. Okay. But this is under a radical and you're adding 1 to it. All that did though was change my negative 1/2 to a positive 1/2. So then I recognize, okay, this is just 3 over x plus 1/12 x times itself, 3 over x plus 1/12 x. If I were to FOIL this out, this is 9 over x squared. I have a x is reduced, positive 1/4, positive 1/4, I add to positive 1/2. And the last terms give me this x squared over 144. So this factors into this beautiful binomial squared. It's called a perfect square trinomial. This pops up a lot with these arc length problems. And it's really nice because all of a sudden I don't have to worry about the square root any longer. They undo each other, polynomial, then some tedious math, and you're done. I'm going to do another example. This time, we're given the function, the natural log of secant x over the interval 0 to pi fourths. Okay, before I even begin, I'm a little bit concerned. I kind of remember from the previous video, the very first thing he did, Mr. Simpson, which is myself, as I understand, is he wrote down the function has to be continuous and the derivative has to be continuous. Well, secant is known for not being continuous. But maybe if we're given this interval, 0 to pi fourths. Let me think about that for 2 more seconds. And then the natural log has its own problems. Let me think about this. Okay. Cosine starts high and does its little wave. So secant looks something like this. And cosine touches 0 at pi halves. So yeah, we're good. As long as I stay below pi fourths, that's plenty fine. So from this is what's described on the secant graph. Now I'm plugging that into the natural log graph. The natural log graph can't be negative and it can't be 0. That's never going to happen here. Secant starts at 1 and goes up a little bit. So it's not going to hit 0 and it's not going to be negative. Okay. I'm now 100% okay with this function. I'm going to find the length of that function, which I do not have a picture of it. I'm not sure what it looks like. But I'm going to find the length of that function from 0 to pi fourths. Easy. There's a formula sitting right above me. I do need, though, the derivative, f prime of x. The natural log of something is going to be 1 over that something times the derivative of the inside. And the derivative of secant is secant tangent. Well, the secant's reduced. F prime of x is tangent. And then I need that value squared. So I'm talking about tan squared. Okay. I think I'm ready for the formula. I'm going to integrate from 0 to pi fourths, square root of 1 plus tan squared x with respect to x. Okay, that looks very familiar. 1 plus tangent squared. That's a Pythagorean identity. That sums up to secant squared. Square root of secant squared is a secant. integral of secant, we struggled with this at the beginning of Calculus 2, but I think we called it like a banana rule, and we have, do you remember? It is the natural log of secant x plus tangent x. And I need to evaluate that still from 0 to pi fourths. All right. If that does not ring a bell to you, go back and find a trig integration video. We multiply by a fancy 1 in order to come up with this. Okay, shoving in pi fourths minus 0. Well, secant of pi fourths, okay, cosine of pi fourths is root 2 over 2. When you reciprocate that, you get 2 over root 2, but you rationalize it, so it's 2 root 2 over 2, it reduces root 2. Tangent of pi fourths is a lovely 1. Secant of 0 is 1. Tangent of 0 is 0. I'm getting these values off the unit circle, maybe you know the graphs. Well, this is just the natural log of 1. The natural log of 1 is 0, so when you subtract 0, that's nothing. So I claim it's just the natural log of, and I'll call that 1 plus the square root of 2. That was fun. You need the derivative. You need to square it. You need to shove it into a formula. This one I didn't have to worry about perfect square trinomials. I just had to know some trig stuff. And I had to know some integration stuff. Easy peasy. Let me see if I can kick out one more example. Okay, that looks hyperbolic to me. I don't remember them exactly, but that's some sort of hyperbolic looking thing. But I've got some function, 1/2 of e to the x plus e to the negative x on this interval, from negative natural log of 2 to positive natural log of 2. Okay, cool. I need to find the length of this curve on that interval. Okay, cool. I'm just going to shove it into this formula. That is, I need to find the derivative. So if I call that f of x, then y prime or f prime of x. Okay, I think I can do this. Oh, I think I'll distribute the 1/2 and then allow it to do that. I think I don't know. I'm going to distribute the 1/2 and do them independently. Oh, I didn't. That's not prime. I was going to take the derivative in that step, but I didn't. So let me destroy the prime and write the prime here. I'm now taking the derivative. The derivative of 1/2 e to the x is 1/2 e to the x. And then the derivative of 1/2 e to the negative x is a negative 1/2 e to the negative x. I think that 1/2 really came from the beginning. I just forgot how derivatives work. Okay, so I'm going to pull out a 1/2, or do I want to? Yeah, I want to pull that 1/2. Okay, so you get the derivative, however you do it. Then you need that squared. So this is the derivative of f squared. It's just that thing squared. I think I'll just acknowledge that I have 1/4 and then 2 of these. So a half times a half is a fourth, and then just distribute this out. I just kind of want it written side by side so I can play with my fingers. All right, e to the x times e to the x, you add exponents, so e to the 2x. And you have a negative. Now if I'm adding these exponents, x plus a negative x becomes 0. E to the 0 is 1, so I'm subtracting 1 more, then I'm adding e to the negative 2x. Oh, goodness. This is the derivative squared. I think I'm ready to now shove that into a formula and hope it works. Okay, the 1/4 may be bothersome, but L will be equal to the integral from negative ln2 to positive ln2 of the square root of 1 plus that. I'm debating if I should distribute the 1/4, because then I could add the stuff. What do I do over there? Yeah, I do that. Because I'm about to add, and I'm going to want to combine these like terms, I'm going to go ahead and fourth all of these values. So 1/4 e to the 2x minus 2/4, which is negative 1/2, plus 1/4 e to the negative 2x with respect to x. All I did was add 1 to this and distribute those force. Now I can sum. 1 and negative 1/2 would be a positive 1/2. I'm going to keep it in the middle. Okay, I claim on the first example, if you can just acknowledge that there's probably a perfect square trinomial in there, everything's hunky-dory. Let's see if I can see it. The first term would be the square of a term, so 1/2 e to the x. That makes sense to me. This would be 1/2 e to the negative x. I just did a minus sign, so how about a plus sign? If this thing were squared, would I get that back? I would get the first term, I would get the last term, but if I multiply them together and add or double it, do I get half? Oh yeah, because 1/2 e to the x times 1/2 e to the negative x is 1/4. I'll have another of those. Double that. You get 2/4, which is 1/2. Bam. Okay. This is a perfect square trinomial. If you don't see it, I'm right with you. Take this, FOIL it out, play around with how we got here. All we did was change that sign, really. So it's the same idea. We got here by squaring a binomial. We altered it a little bit, and then we could factor it. All right. But if I can rewrite it as something being squared, then the square and the square root cancel each other out, and I'm just trying to integrate along that interval. A half e to the x plus a half e to the negative x. I can do that. The arc length calculus 2 part is over. I'm now just doing some arithmetic. The integral of e to the x is simply e to the x. The integral of 1/2 e to the negative x is simply a negative 1/2 e to the x, negative x. Integrate that thing from a negative ln2 to positive ln2. Ln's go nicely with these e's. So I have 1/2 e to the ln2 minus 1/2 e to the negative ln2 minus 1/2 e to the negative ln2 minus 1/2 e to the negative ln2. Probably would have been smart to take out a 1/2, but I forgot to, so I can deal with it. E to the natural log of 2 is just 2. Now I can't really do the same thing here. The minus sign kind of gets in the way. But what we can do is we can kick that -1 coefficient up to a power of this 2. So I have 2 to the negative first. So negative ln2 is the same thing as ln of 1/2. You take the coefficient of -1, you put it as a exponent on the argument 2, so you have 2 to the negative first power. Negative first power just takes your base and reciprocates it, so the 2 becomes 1/2. Now, e to the natural log of 1/2 is 1/2. Similarly here, e to the negative natural log of 2 we just said is 1/2. That's going to make it a positive ln2, so this is just 2. All right. I did it different in my notes, but I think it's going to come out okay in the end. This is 1 minus 1/4 minus 1/4 plus 1. So I get 2 minus 2/4 or 1/2. I get 3/2. All right. So arc length, I claim it's an easy lecture. You just find the derivative, you square it, you shove it into the formula. The hard part may be recognizing those perfect square trinomials, but you just play with it, just factor. You got this. See you next time.